Hello to all of the people who are interested in knowing about flow rates. Today, we will be discussing flow rates in a PowerPoint presentation, the flow rates in and out of pneumatic actuators. That's funny. Okay, guys, here we go. Yeah. No, for real, that's what we're actually going to do. Yeah, that was good. Yeah. I can do it up. I can do it. Here we go. Okay, so yeah, no, flow rates are really cool. Actually, let me just do a demo here. You know me, I've always got one of my cylinders ready to go. Okay, good. This is really simple. This is stupid simple. I have an operation. Okay, I have an operation. I am an actor. So, okay, here we go, guys. I have a pneumatic actuator, and this pneumatic actuator has to apply a certain amount of force, whatever. We don't care about the force. Actually, we really shouldn't talk about the force at all, other than one example where I want to give you kind of a practical example about selecting a force and choosing the pressure when we're selecting force. Selecting a cylinder, selecting pressure for a particular application. Pardon me. Other than that, I don't want to talk about force. I want to talk about how much air is required to make this extend. Okay, so now, interesting point here. You guys know when we talked about actuators, we had kind of two different extensions. One was, this is an application maybe where it's lifting a table or lowering a table. So the table's here, and then whoop, it lowers, and then it rises and lowers. That application, the rod travel is equal to the stroke. In that application, the distance this thing travels during the application, the rod travel is equal to the stroke, up and down, up and down. But in some situations, we may want to use this cylinder or another one in a clamping application. All right? So I need to clamp onto this so that I can drill a hole in it or something. So here we go. I have this. It comes on an assembly line. It comes down a thing, and all of a sudden this goes, right? And it kicks it out a little bit, but it doesn't go all the way. When we clamp onto something, the cylinder doesn't extend all the way. It extends all the way minus just a little bit. Just a little bit. I don't know, whatever, like just half an inch or something. Depending on how much this thing is going to deform when we squeeze onto it. It may deform to some degree. So my extension distance during the operation, the operational extension distance, or what we call the rod travel, is different in a clamping operation. So with that said and done, during this operation, whether it's the rod travel is the full stroke or whether it's the clamping distance, during that operation, I need, here we go. I need a certain amount of air to do that. So that air needs to come from somewhere, and we know it comes from a compressor, which we don't know much about, but we can just imagine that. It comes from a compressor. Okay, so that's a certain amount of air. Well, guess what? If I needed this cylinder to do the same thing, right? The same pressure. Let's just even say that this cylinder is the same bore diameter, okay? Same bore diameter, but obviously the extension is much longer because the stroke is much longer, and this thing goes out to here. Or if it's the clamping distance, it goes out to here. But as we know, dude, there's a lot more volume here. So with that said and done, we're going to study that. We're going to study the volume, and we're going to study the consistent use of that volume, which we'll call flow rate. Okay, good. So with that said and done, let's jump into the PowerPoint. Okay, here we go. Flow rates. Welcome to flow rates. This is a really cool flow rate chart, and I will show you a little bit about this flow rate chart here, and let's take a look at it. Oh, so it seems as though the volume of air, which is along here, in cubic feet, the volume of air in cubic feet. I wonder why we do it in cubic feet. I mean, it kind of sounds a little silly because these numbers are tiny. Cubic feet, the numbers are tiny. I wonder why they use cubic feet. Huh, that's weird. Oh, well, I guess it's a mystery. Let's move on. Okay, good. So now this is the length of the stroke, and we can see the stroke is longer and longer and longer. Technically, this is talking about cylinders that have the rod travel equal to the stroke, okay? So that's the length of the stroke, and then we can see this for a 6-inch bore all the way down to a 1 1/4 inch bore. We can see the volume displaced in cubic feet. It goes up and up and up, and it's actually linear. It's linear, okay? Because as we see, we're not changing this along here is a changing stroke length and not a changing bore diameter. If we put the bore diameter here, these guys would be curved because we're dealing with the bore diameter squared. So with that said and done, I will go back and I will do the volume of air in cubic feet. You know what? I'm just going to stop and pause here. I'm going to leave the mic open. Okay, open mic time. Does anyone have any idea why it uses cubic feet and not cubic inches? Because, you know, if the bore diameter is in inches, or say millimeters, which is pretty general, why would we want to do flow rate in cubic feet?
Time.
Okay, so,
Cubic feet per minute. The volume per time.
Right, absolutely. So what's going on? That's a flow rate. Yeah, the standard way that we look at the displacement volume in pneumatic systems is in cubic feet, actually. We calculate it in cubic inches, and then from there we convert it to cubic feet, because when we go and study flow rates, we actually study it in cubic feet per minute. Because if you take a look at the flow rate, right, this is actually pretty important, and I think this is a good one. Okay, so this is 0.1 cubic feet. I mean, I don't know what it is, but it's pretty small. So if this is going like this, how many times is that going to happen in a minute? Well, if I'm doing it once a second, it's pretty much going to be like, you know, whatever. It's going to be 6 cubic feet or something. It's going to be some larger number. If I'm doing this slowly, right, and I do this so many times in a minute, and they have 3 of these or 5 or 6 of these in a system going, and I have 1 compressor running it, well, the total amount of volume displaced in a minute is going to be in cubic feet, even though this is just 0.1 cubic feet. So yeah, when we talk about flow rate, when we're after the flow rate of pneumatic actuators or of a pneumatic system, usually it's got many actuators and they're going back and forth and they're moving all the time. Then we end up looking at values like 5 or 6 or 2 or 3 or 4 or 10 or 12 or 15, possibly 100 cubic feet per minute. 100 would be something like running a whole factory, like hundreds of pneumatic actuators. So with that said and done, let's jump into the PowerPoint, and then I will talk to you guys about the PowerPoint. Here we go. We have to press the button. Where's the button? There we go. Welcome to flow rates. Okay, here we go. So what we're going to be discussing is the displacement of volume during application, during the extension and retraction. So I talked about that. I showed you practically with that cylinder. And the flow rates are required because what's happening is that those actuators repeat their actions all the time. If an actuator just goes out once in an hour and then maybe goes back in an hour, there's such a ridiculous, we don't even consider a flow rate. What we're looking at flow rates for is actions where they're consistent, the cylinder going back and forth continuously during an operation. And then from there, we can actually select the required flow rate. It will help us select a compressor. And right now, we're just going to kind of look at selecting compressors on really basic stuff. We're going to get into a whole lecture on selecting compressors. For now, this is why we need to understand what flow rates are. So we know all about the dimensions of a cylinder. What I need to do is introduce some new symbology to you guys, and it's the volume displaced during operation. Now, the term displaced is a little bit odd in that what's going on is that the volume that goes in here, so I mean, when this extends, when it starts retracted, and I put air into this side to make it extend, I'm putting air into here. So it's kind of weird to think that that's not displaced air. That's air that's being put in. Well, the fact is this cylinder then has to retract at some point, and it takes all of this air and it displaces it into the atmosphere, and then it's gone. So essentially, we're really calling it displacement, even though it doesn't get displaced till later. But as soon as we put air into a cylinder, it's gone. We've used it, and at some point it will disappear and we'll never use it again. It just goes into the atmosphere. So essentially, the air that we put in there is like we're displacing, or more specifically, you can think about it like this. If this cylinder were to extend, if someone pulled it, then what's happening is it's displacing the air that's back in here, this little tiny section here. When this extends, it is going to displace a bunch of area or volume that's in here. Either way, however you want to look at it, the term is to displace air. So we're going to say this is a capital D with a lowercase capital E as a subscript. And guys, I do not want to see any more in your work in the assignment where we're going to do the bottling station assignment. When you're doing your calculations, I would not like to see anyone using not using subscripts and superscripts properly. Please don't do that. I've just had enough of that. Sorry, I will move on, okay? Because you guys learned that very well last semester in 110. Okay, guys, so there you go. That's what this is all about. And essentially, this is a really complicated formula. This is going to blow your mind. It is area times distance. Yeah, no, that wasn't too complicated. Dude, it's just it's the formula for volume. Volume is height, whatever. The volume is area of one side times distance, or length times width times height. And guess what? Length times width is area. So I don't think that's a big surprise. This is a three-dimensional space, and when all of this air is displaced, and I want to calculate how much air is displaced, I multiply the distance this rod travels. Now, it's interesting. It says, displacement here is where there is no rod at all. Now, the displacement retraction is actually different. Just like the displacement, just like the force for retraction is less, the displacement for retraction is less. It's a smaller volume because the rod is in the way. So with that said and done, that is the formula for displacement. Sorry, this is the formula, and that's the formula. Really basic formulas. And when you guys are doing your work, I need you to use pi, because all of the calculations for the quiz are based on pi, not 3.14. So if you don't have pi in your calculator, deal with it. Find out what pi is. You should know pi to at least 5 or 6 decimal places, I imagine. If not, go look it up and program it into your calculator as one of the memories so you can just type it in, because I need you to use either the symbol pi on your calculator, or actually go ahead and put in the value of pi in your calculations. And you want to type in that. You don't want to type that in every time, so use the memory in your calculator. So with that said and done, I'm going to move forward. Okay, good. So that's how you calculate it, and it's no big deal. And there you go. Moving forward here, I need to talk about flow rates. Now, as I mentioned, we're talking about flow rates, and essentially what I need you guys to do is understand that flow is, when we're talking about imperial, it's cubic feet per minute or standard cubic feet per minute, and the symbol for flow is Q. So this is a whole new thing. The symbol for flow is Q. You have to wrap your head around that a little bit differently. It used to be, when we studied electronics, it used to be for charge, but in this case, it is for flow. Okay, pretty standard flow symbol for physics is a Q. Okay, good. So the symbol unit is this, although this is the acronym for the unit at the end, or more specifically, these two different units, or these two different acronyms, describe cubic feet per minute. That is the actual unit. I want to see this unit in your calculation. I do not want you to put these acronyms in your calculation. So I want to see this in your calculations. But the fact is, this is cubic feet per minute, and this is cubic feet per minute, although this is standard cubic feet per minute, and this is cubic feet per minute. This is very much kind of in the same way, talking about like when we talked about PSI, PSIG, or PSIA. Essentially, they all stand for the unit cubic feet pounds per square inch, but it's a different way of looking at it. So we can take a look at flow rate from two sides of the compressor. Yeah, from the air that's actually being compressed, or pressurized air. So when we talk about cubic feet per minute, in pressurized air, we just call it CFM, cubic feet per minute. When we talk about standard air, and you guys remember what standard air is from lecture 1, it's just the air in the atmosphere. When we talk about standard air, Now, standard air has a very particular value to it, but generally in pneumatics, unless we're talking about extremes, like we're up a mountain or we're in, in a low pressure environment, like if we're in the atmosphere in the space shuttle or something, or the International Space Station where the pressure is a little bit higher, generally standard air has a very particular value, but that in this term, when we're talking about standard air, it's just the air in the atmosphere of generally when we're at sea level. Okay, so good. Standard cubic feet per minute is STFM, but they're both in cubic feet per minute. Now, standard air is just atmospheric air, and that's the air that essentially is being sucked into the compressor. Now, the interesting thing here is that the same amount, the same amount of air leaves the compressor, but because it has been compressed, its volume is less, and we measure cubic feet per minute in volume. So therefore, if I had 1,000 moles of air going into a compressor, I may only get 300 moles of air leaving the compressor because they have been compressed, or I may only get whatever 1 or 2 moles. What's happening is that the volume of air, I apologize. I just totally steered you wrong, because a mole indicates a certain amount of molecules, but I was thinking about buoyancy and I was thinking about pressure when we have a mole. So just cancel what I said. If I had, let's just say 100 cubic feet of air that went into my compressor, and my compressor had a 1 to 10 compression ratio, I would then only have 10 cubic feet of air leaving my compressor, and that would be the pressurized air in the system. Okay, yeah, okay, good. So when we're talking about flow rates, there are two things. When we calculate flow rate, dude, this volume calculation is not enough. I think that makes sense, because volume doesn't help us. Flow rate is cubic feet per minute. So we need both extension, so we need full displacement for both extension and retraction, and we need cycle time in minutes. Okay, so because we're calculating the displacement of the cylinder in cubic feet, and we're talking about how long it takes to displace the cylinder, and that is going to be in minutes because it's cubic feet per minute. Now, mostly we're going to be given information in cubic or in inches. We'll be calculating cubic inches, and we're going to be talking about cylinder actions in seconds. So we have to do some conversion, but I've got a formula that does it for you. Moving forward, okay, good. So the timing for calculation flow rate, it's considered, okay, from two different angles, okay? So what's going on is that if I'm taking a look at a cylinder in a process, it's going back and forth and back and forth and back and forth and back and forth. If I know the number of cycles that cylinder takes in 1 minute, so it takes 30 cycles in a minute, okay? And then we could say it cycles every 2 seconds, but let's just say it did 30 cycles per minute, and I knew the total volume it displaced over 1 minute, then I could calculate the flow rate, and I think that makes sense to you. Now, that is maybe more of a specialized situation where we have a cylinder that makes a very specific amount of cycles per minute, very close to the minute time, and we can calculate its volume. But often what we have is we have a bunch of cylinders in a system. Hold on, I just want to share you me. Okay, good. We have a bunch of cylinders in a system that are doing back and forth, and one is doing this maybe 5 times a minute, and one is doing this, stands up for 30 seconds, and then comes back, and then maybe for 45 seconds it stands out, and then it comes back for 2 seconds, and it goes out for 45 seconds, and then back for 2 seconds, and out for 45 seconds. Well, you can't just say, well, how many is it doing per minute? Well, it's doing like 1 point something per minute. No, we're looking at examples here in the first situation where we know exactly how many cycles it makes per minute, and we know how much displacement, air's been displaced through that whole minute. You know, that happens sometimes. But if we have multiple cylinders doing multiple things at different timing throughout a whole section, and some of those timings of those cylinders is like, you know, some weird thing where it's not a certain amount of cycles per minute, then there's another way to deal with that. And we just kind of take a look at differently. So let me just share my screen again. Here we go, share screen. Here we go. So the other way to look at this is use the time from the start of one cycle of an actuator to the beginning of the next cycle of an actuator. Okay, so the cycle concept we'll get into in a minute. What's important is the turnaround time, right? So it could be that a cylinder extends really quickly and it stays there for a minute, and then it retracts, extends, retracts, extends, retracts, extends, and then it stays there for a minute and then goes back and forth and back and forth. So the cycle time essentially is the time it takes for the cylinder to extend and retract. But we have to take into consideration that there's this pause time before. It may not extend, retract, it may extend, sit there for a certain amount of time. And it may take, actually, it may take 2 or 3 seconds to fully extend, and then it sits there for 10 seconds and it retracts really quickly. So all of these things are important, and there's a kind of a mathematical way of looking at this, and let's take a look at this. What we're going to do is we're going to do some definitions of some time and some turnaround. Okay, so the time that the cylinder takes to extend is important. It also, by the time the cylinder goes out and then turns around and gets all the way back, that's one full cycle. Okay, so it goes all the way out, it stops, it turns around, it comes back. Now, the turnaround time is very important. It's the length of time that it pauses either out here or it pauses in retraction. So we've got this extension time, this retraction time, and this turnaround time, and we'll see that work out in a little chart that I'm going to show you guys. There's an example here. A bottling machine has 2 cylinders, cylinder A and cylinder B. Cylinder A extends to clamp the bottle. Okay, so bam, it clamps the bottle, and that's just extended. It takes barely any time to extend, probably like a quarter second, and then it just sits there. Okay, then cylinder B extends and punches the cap, and then it retracts, and then cylinder B retracts, and then cylinder A retracts. Okay, so that is, this cycle is continuous. It just happens continually, back and forth and back and forth and back and forth. Now, there's probably some kind of pause time before this, but what we're going to do is we're going to write the control statement down. This will help us define the times. Now, for here, I've extended some of the time, so we have an example here. Cylinder A extends and holds the bottle for 2 seconds. Okay. Cylinder B extends and retracts over 1 second. So whether it takes 3/4 of a second and a 1/4 second to retract, it doesn't matter. It says here it extends and retracts over 1 second. Okay, so one full cycle takes a second. Cylinder A retracts and waits for the next bottle for 1 second. So 1 second is my turnaround time. Okay, so that, you know, that you may be able to visualize that, and like if you had a couple cylinders in your hand or whatever, you could kind of simulate it, just moving them back and forth. But let's actually put it into an example and take a look at a little bit of chart here. Now, I have some numbers here. I know that the turnaround time for my B plus and B minus is 1 second. So I'm going to label that 1 second. And I know that the full cycle time from A plus to A minus is 2 seconds. So I write my control statement down, and I do a couple little dots in the middle. I create some space, and then I write my control statement again. Now, with that, I am able to get the full T, or the cycle time, the amount of time it takes to go out, pause, and come back. Okay, good. So this is not complicated. The only thing you need to know is just kind of practice this, because, pardon me, these different descriptions will change depending on the application. The wording will be different, and some of these, in this case, we didn't say cylinder B extends for 1 second and pauses for 2 seconds and then retracts, and it takes a 1/4 second to retract. But if we did say that, we could fill that stuff in here. That type of information can be filled in this time chart. This is a basic time chart, and essentially what we're looking at is a total time. The cycle time is 3 seconds. So here we go. The sequence time and the delay time. The sequence time is here. look at this is the control statement. This is the sequence. The delay time is the time in between. So Armit, you have your hand up. Please go ahead.
Yes, Professor. I was just wondering, shouldn't the delay time between B plus and then B minus? I mean, okay. No. Yep. Shouldn't it be between A plus? Yeah, that is okay. I just got a misunderstanding. I'm sorry.
You mean it should be in here? Yeah.
No. I thought it shouldn't be between B plus and B minus, where you have labeled 1 second.
Yeah, but that's here. You see, look, cylinder B extends and retracts over 1 second. Do you see that?
Yes, I do, but I'm just a little bit confused about this delay time and.
Okay, so let's take a look at this. We'll step by step. Cylinder extends and holds the bottle for 2 seconds. Okay, so cylinder A extends and holds the bottle for 2 seconds. Okay, so it doesn't tell you how long it takes to extend. It's just assuming it extends really quickly, and it holds it for 2 seconds. Now, during that 2 seconds, cylinder B extends and retracts over 1 second, because we know that's happening in between. So cylinder B extends and retracts for 1 second. Now, if we go back to here, we can see that cylinder A retracts here. This is cylinder A retracting. And then it waits for the next bottle for 1 second. That is the turnaround time. So your turnaround time is here, or the delay time is here, because that delay time indicates that there's 1 second that it's waiting for the next cycle or the next bottle. So when the next bottle comes, this cycle happens all over again. So it's just a matter of.
I was just mixing up this delay time with that turnover time.
Okay, yeah, turnaround time and delay time are the same. It's just another way of looking at it. So I need you guys to get used to looking at different terms to discuss that. But I think turnaround time and delay time, it just makes sense. The turnaround time is when it happens like all over again. So once the cycle is completely done and once the delay is done, then that's considered 1 cycle time. But that's the delay time in here. So, okay, there you go. So essentially, cylinder 1 takes 1 second to extend and retract. The cycle time is this, blah, 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 adding. Okay, so the total is 3 seconds. And I think it's just simple. It's just adding all of this. And by the way, this guy doesn't really matter. I mean, we have to put it in, but it doesn't actually affect anything because there's no waiting in between here and waiting in between here. It just happens. And that is just a matter of thinking about the actual application. It's good to visualize it or draw it to understand what's actually happening in here. Now, we'll take another example here. It's just, we got to take these words and we have to turn it into this time chart here. Okay, good. So cylinder A stamps an image onto a piece of paper. It extends and retracts in 1/2 second. So bang, bing, bang, up, down, like smash, down, and then back up again. Cylinder B pulls a tray out and waits 3 seconds for the paper to be removed, okay? And then a new piece of paper is placed into the tray. So it takes 3 seconds for an operator to pull the paper out and put a new piece of paper in. And cylinder B then extends again quickly. So just from this description, I can write down my control statement. Don't worry about the timing. Just write the control statement, write a few dots, and then write the control statement all over again. From there, identify the times that are discussed and also identify the delay time and just label them and then add them all up. It's just that simple. This plus this plus this plus this. You don't even have to, show the formula per se. I mean, you say that the TC is equal to this plus this. If you draw it like this, you can just write the answer down. Unless it gets really complicated, then you can use a formula that says TC equals TS plus TD, or delay. Okay, good. So the total cycle time is 3.5 seconds, and it makes sense. I got all of these things from this example. Cylinder A stamps the image on the paper. It extends and retracts in 1/2 second. Half a second. Now, then cylinder B, it just says, then cylinder B pulls a tray out. So it doesn't say how long it waits for this to happen. And we have seen when we looked at sequencing of cylinders in lab 2 that if cylinder B extends after cylinder A extends, it happens immediately. Now, if it did discuss, it waits for a certain amount of time before the next cylinder makes the next action, then you can put that delay in there. You could put a delay in here, but it's not discussed. So we just say there's 0-second delay. Then it says that this happens, it extends and retracts, and it takes 3 seconds. Now, as far as the turnaround time, so how do we know how long it takes? Hold on, we got a good question here. So wait a sec. How do we know how long it takes for B to extend and retract? So what's happening is that's a good question. If it doesn't say how long it takes a cylinder to actually move out and or move back in again, what we do is we consider that kind of void or just nothing. And the reasoning is this. We essentially, void is, we just don't put it in the formula, and it's because of this. From here, okay, so let's say this, I'm going to start counting. 1, 2, 3, I'll do that quicker. 1, 2, 3. Okay, it just extended and retracted, and it took 3 seconds to do that. But whether it goes like this, and it does that in 3 seconds, we don't really care how long it takes to extend or how long it takes to retract. We know that it displaced a certain amount of air in 3 seconds. So whether it does this or displacing the same amount of air in 3 seconds. So it's okay. But sometimes we have to do that. And there's an example here where a cylinder takes a long time to extend. And it's just a matter of just writing it down in your time chart. Okay, here we go. So continuing on. Whoa, I almost ran over Val. Twice. Wow. I almost got you. Okay, hold on a second. I probably ran over you before, Val. So, yeah. Yeah, she's pretty quick. Okay, here we go. All right, so there you go. There's that example. Let's take a look at another. Oh, dude, this is getting really complicated. All you have to do is write your control statement down and start labeling everything. And then you can just find the total time. So we're going to define the cycle time, and by adding the delay time, oh my, with the sequence time, pardon me, and then we'll do our thing. Okay, good. The description. Now, in lab 2 and in lab 4, you have got practice taking the description of an action of a cylinder and writing the control statement. You guys need to do that, and I want you to continue to do that forever and ever and ever, because writing a control statement down, but just stop the stupid mouse, is really very powerful. Now, we have an example here where it does take a certain amount of time for a cylinder to extend. There's a delay, and then there's a certain amount of time for a cylinder to retract, and then there's no delay, and let's continue on. So all we're going to do is we're going to take a look at the description, and then we're going to write the control statement. We're going to label all the times. The cylinder retracts slowly to open a lid of a machine press. Okay, it takes 1 second. So it's doing this slowly because it doesn't want to open the lid like, right? There are always lots of examples where we may want a cylinder to be metered, which is going to make the cylinder slow down a little bit. As soon as it fully retracts, a robot moves, okay? A robot moves and it places a part, okay? That's cool. And new part into the clamp, and 2.5 seconds. So essentially what's going on is that the cylinder retracts, opens up this lid. The robot needs to go and do something. It needs to remove the last part and place a new part in. So it goes, it reaches in to this area, grabs a part, pulls it out, and then grabs another part and drops it off. And robots can move really quickly. It takes 2.5 seconds to do that. So then what happens is cylinder A extends and closes the door. Okay, so it's actually going to extend and close the door slowly, a little bit more slowly than it took to open it. And it could be that maybe there's a new part in there and that it's a little fragile, and that whatever, the door has to be closed a little bit gently. However it is, it takes a little longer to extend this time. So we're just going to write that down here, 1 second here for full retraction, and then there's a 2.5 second delay while that robot does its thing, and then there's this extension, and it's a little bit slow. Okay, good. Now, once the door is closed, I press cylinder B and C, okay? So it looks like there's 2 press cylinders, maybe from either side, to really press hard, extend quickly, so just bam, they extend really quickly, and then they retract, okay? So bam, bam. All right, well, there you go. So, and that whole process takes 5 seconds. So we can write that down. This happens and this happens in 0.5 seconds. So just in half a second. So it looks like whatever's going on in there, these 2 cylinders are pretty much just going bam, bam, like they're smacking into the thing. Maybe they're like, you know, squeezing or pressing something inside that part. Whatever that robot put in there, it gets a whack from 2 cylinders, bam, right? Then it delays for 5 seconds. It just kind of sits there. And there's a reason it has to sit there, because we whacked it so hard that it actually generated some heat, right? Because it got squeezed. So you know what? Let's just let it sit here and cool for 5 seconds before we actually start the whole cycle again. And once it's done, what's going to happen is the whole thing's going to happen again. The lid's going to get open. The robot's going to grab the part, put a new one in, close the door, bam, wait 5 seconds, and do the whole thing again. So a little bit more complicated, but all you do is write the control statement down and then label all the times and then find out your sequence time. Add some delay, press play, get your total. There you go. So nice and simple. That's your cylinder time. Now, we are now experts at understanding how to calculate how much time it takes for some cylinders to do their thing and fully have 1 cycle time and a delay time and then go on. Okay, good. So what's happening here is that when we know that, we have the time it takes for 1 cycle, and we know the actions of the cylinders, and we can calculate the volume that each cylinder displaces during its entire process. So a cylinder is going to extend and retract, and we can calculate the amount of volume displaced during that extension and retraction because we know the parameters. I mean, we can calculate DE and DR because we've got the formulas up here. And they're not complicated formulas. This is D and this is DR. Well, it's jumping around. I don't have my mouse. This is D and this is DR, right? So we know these values and we can calculate them directly from the information of the cylinder because we know the size of the cylinder and we know the rod travel. It may not be the stroke, it may be the clamping distance, or it may be the stroke. But the rod travel is the number we're going to put in there, not the stroke value. But again, sometimes rod travel is the stroke, and it is a matter of looking at the description and the operational parameters. Okay, good. So here we go. Essentially, what's going to happen is that we take this value, which is in cubic inches. We take this value, which is in cubic inches, and that's the total displacement of a cylinder in extension and retraction. And if we divide it by this, it turns it into cubic feet. Okay, well, that makes a lot of sense. Okay, just hold on to this thought. You don't, guess what? You don't even need this formula. You don't need it unless you really need to calculate it for some reason, but don't worry about it. Here we go, cycle time. Well, we know that the cycle time is this, and we know that, you know what, if we wanted to calculate this 3 seconds in minutes, we can divide that by 60. Okay, well, maybe there's like some way we can put all of this together. Okay, here we go. Let's take a look at this. Now, this is my new formula here. And this formula is the formula for Q, which is a flow rate. And dude, you have no idea how cool this is, this Q is, this full flow rate formula when we get into the gas laws and when we get into selecting compressors and we look at power factors. This formula is so cool, and this Q symbol is like the little answer to so many cool things. Let's just roll with it. Because you know what? Q has got time in it. As soon as you put time into a formula, it's really cool. Okay, so here's the displacement divided by time, which is a flow rate. And this, in this case, I'm going to do displacement, and I'm going to multiply it by this number. Now, that number is not this number. It's a different number. Essentially, what's going on is that this is a factor that converts this cubic inches into cubic feet, and this time into minutes. That's all you need to do. Sorry, I'm jumping around. I'm going to put this in cubic inches. I'm going to put this in cubic inches. I'm going to put this value in here in seconds. I'm going to put this number in, and the answer is going to be in cubic feet per minute, because this is a conversion factor that's just in the formula. Okay, good. So there you go. So this is an example. Now, this is important that you guys watch this, because the quiz may lean on this a little bit. Okay, so here we go. So this is what's happening here, is that we're looking at how much air this thing, the flow rate required to drive this cylinder. Now, in this case, the rod travel is equal to the clamping distance, not the stroke. Here we go. So there's a description of the operation. Okay, we've got the bore diameter, rod diameter, and stroke. We've got clamping distance, and we're dealing with 100 psi G. If we wanted to, we could calculate the force. But here, what I'm saying is that the cylinder clamp molds, it holds for 10 seconds, okay? And then it fully retracts for 2.5 before doing the whole thing again. So what's going on here is that this guy, the cylinder clamps on the mold and holds it for 10 seconds. So it doesn't say how long it takes to clamp it. So we can say that that happens instantly. Holds it for 10 seconds, and then it fully retracts. So we can say that it retracts really quickly, and then it waits for 2.5 seconds. Oh, there are 2 delay times. Oh, that's complicated. What does that look like? Dude, it's okay. You can just calculate it in your time chart, and you can put a delay time before. You can put a delay time in here, because there are 2 delay times. Okay, good. So there we go. What I'm going to do is you guys know how to calculate the force, and the reason I'm doing this is because there is here's the force in retraction, and there is an example here that I wanted to go over, because I didn't use this example exactly in when we talked about actuators. So I'm going to stick this into the actuator PowerPoint, but I need to just hold on to this, guys. Where are applications where you can, okay, there's a question here. Yeah, extend the rod slowly. Yeah, sure. That application right here. Here we go. Here's an extension. This extends slowly and that retracts slowly. So that's the answer to your question. Okay, good. So here we go. So I have done some calculations. I've calculated the force in extension. I calculated the force of retraction. And there's a reason I did. Watch this. Okay, so we know that when I calculate this force, the retraction force is 235 pounds. The extension force is 314 pounds. Okay, good. So if I had a cylinder with the 2-inch bore cylinder, and I wanted my PSI was 100 PSI, and I had a 2-inch cylinder bore, it would generate 314 pounds of force. Okay, what if I needed 350 pounds of force? What are my options? I need 350 pounds of force, but this thing will only apply 314. What do I do? Floor's open. Increase the pressure.
Take a bigger cylinder.
What's that?
Take a bigger cylinder.
Yep, absolutely. We can do a bigger cylinder. Absolutely. So essentially, our 2 options are this. Bigger cylinder. Wait a second. Solution, use a higher pressure. Recalculate for 115 PSI. Yep, that's definitely one. Somebody mentioned that. The other is use a greater cylinder, a cylinder with a larger bore. Okay, we can do that. So we can do both for sure. Now, if I needed exactly 150 PSI of clamping force, I may be recalculating for a bore diameter. No, a bore diameter that has a very unique bore. But I'm going to say, Sonal, you had mentioned a cylinder with a smaller rod. But look at this. What we're doing is we're talking about the mold requires 150 of clamping force, and the clamping force is here. Clamping force is here. So this is the force in extension. So if I change the rod diameter, it wouldn't, I don't care, because I'm only after the diameter here. Right. Okay, good. So I can do that, or I can recalculate this. Now, essentially, if I need exactly 350, that may be okay. But what's happening, I mean, if I need exactly hit 350, it may be a problem. But if I could go one way or the other, it wouldn't really matter. But essentially what's going on is that it's a lot easier for me to go and just crank up the pressure a little bit more than it is for me to go out and buy a cylinder that's a little bit bigger and recalculate. Because if I were to just play around with the pressure and then look at the, if I put a recalculated for that pressure, I could put the pressure, I could just simply turn the dial and crank the pressure up, and then I would be able to tune it to exactly 350. But if I was stuck with only 100 pounds of force, I mean 100 psi, if that was my limit, absolutely, I would go out and I would get a 2 1/4. And guess what? If I had a 2 1/4, I'd probably be a little bit more than 350. So I might even lower the pressure a little bit. Or maybe if I had a 2.5 inch cylinder in my stock, I would go use it. And then I would then decrease the pressure so that it would meet exactly 350. And you guys know how to do that math because we did that in week 2. How does a larger bore diameter help? Won't that decrease the pressure inside the cylinder? Oh, this is a great question. That's a great question. Okay, here we go. The question is this. I really want to stop on this. It's good. It's good. So, Sana, what you're doing is you're doing something that kind of makes sense to me, and I remember kind of thinking this in the same way. What's happening here is that if I increase the larger diameter, okay, the bore, if I increase the larger diameter, the volume increases. And I did say at the very beginning of the lesson that depending on the flow rate, if the flow rate is higher, the pressure drops a little bit because I'm having to actually deal with a larger volume of air. But the thing is, that's only during extension. Once it gets to the end, this area, this volume in here is pressurized air equal to system pressure. The actual pressure drop is only during extension and maybe for like a millisecond, a few milliseconds after extension, because then this it pressurizes really quickly. So what you're saying here, Sonal, the question was, wait a second, if I used a larger bore diameter, wouldn't that decrease the pressure to a very small degree? Yes. During extension, absolutely, it would decrease the pressure. But you know what? The force application is only, I'm going to back it up a bit because it's clamping force, right? It's only right there, right at the end. When it finally stops, then the pressure in here builds up quickly, very quickly, and then it meets the system pressure. Whatever your pressure regulator is set to, then it meets that. But during extension, there's a lag in pressure because there's a flow rate in here feeling this great chasm. And if that chasm's bigger, the lag in pressure is even more. But ultimately, the application force, it happens when it stops. When it stops, that pressure goes right up to system pressure. So great example. I really love that discussion. That was great. I hope that answered that question. How you doing, Val?
Really good.
Awesome. You're learning about pneumatics and stuff? Okay,
Yeah.
Ian, go ahead. Yeah, go ahead, dude. Talk.
Sir, this might sound strange. What is going to be the difference? I mean, is there going to be any difference in the displacement if we use this, like the smaller piston and just crank up the pressure, or using a bigger? Because I mean, it's small, but the pressure is going to be bigger, so there's technically should be like the similar amount of molecules of air. Am I right or wrong?
Okay. What you're talking about is essentially going back to the number of moles. And, pardon me, what we do is displacement is not how much air or how many molecules of air. The displacement is the volume of the air. So cubic feet per minute, if it's a very, very, very low pressure, let's say it's like 2 psi A, like we're like the atmosphere on Mars, which is like 0.1 psi A, right? It's really, really low. Doesn't matter. If we were to study the flow rate of air, let's just say the wind or whatever, it's actually volume per time. It's not how many molecules. So yes, absolutely. If we had, let's say, a higher pressure moving a cylinder back and forth, and then we move that same cylinder back and forth with a lower pressure, the flow rate would be exactly the same, although there would be different amount of molecules, because under pressure they're squeezed together and they're compressed. So essentially what we're doing is we're looking at the volume and not the number of molecules.
No, my question was basically related to the, so yeah, we use a bigger cylinder, but then we might needing a bigger compressor in some cases.
Yes.
And that's why I was asking, like, what is the relationship? What is the difference?
Absolutely. So essentially, this is great. So what you're saying is that if we used a larger cylinder, then we would have a greater flow rate. And the answer is, yep, absolutely, we would.
Yeah.
That's definitely in consideration. So, but the thing is, get this. This is kind of weird, but if we change the pressure, it also changes the flow rate. But don't ask me about that right now, because you guys don't understand the gas laws yet, and we will study that in depth when we get into compressors. So yes, you're just kind of just touching on a little bit of the gas laws when we get into compressors, and we'll see, you know what, yeah, all of these things have to kind of give and take a little bit, but for now, we're just going to say the pressure doesn't actually, whatever the pressure is, the flow rate is going to be whatever the flow rate is. Like essentially, you just set the pressure to the same, and then you study the flow rate. If for some reason you went ahead and you took the whole system, you calculated everything, and then you went and changed the pressure, yeah, the flow rate would change. But I don't want to tell you that. I didn't tell you that, right? So,
okay, thank you.
If you have a larger cylinder, it would take a longer time to extend. Yes. Yeah, Dennis, I love it. So if I have a larger cylinder, it will take a longer time to extend, absolutely, especially if it's got a lot of back force. If it's lifting something up, think about it. If it's lifting something up, I mean, I could demo that right now with my compressor. I've actually put this thing on, so I've got, oh wait, no, stop, just stop that. Okay, so let me just, because if I had taken this off, it would have just like, yeah, we would have had hose whip. Okay, so here's the extension. I'm going to do retraction. Okay, here we go. So what I'm going to do is I'm going to pick something up. I can do this. Okay, here we go. Here, this is kind of good. Here, now watch this. I'm going to make this lift up. Now, this has a certain amount of force on it, right, to make it come up, because essentially there's a weight in this rod. Now, I'm going to use a pressure of, wait, here we go. I'm going to be using this pressure, really low pressure. Okay, that's it. You see it extending? Okay, so I'm using a pressure of, I don't know what it is, but it's ridiculously low. Okay, wait, I'm just going to do this, let it retract. Now, I'm going to use a much higher pressure. Okay, so it went up more quickly. So yes, absolutely, depending on the pressure, the cylinder move at a different rate. But also, get this, when I'm using a larger cylinder, the flow rate required to make it happen is going to be the same. So because the flow rate's the same, right, what's going to happen is that it's going to take longer to do it, because whatever the system is, it only has the ability to produce a certain amount of flow rate. If the cylinder is much, much, much bigger, it's going to, like if the cylinder was like a diameter of like this, and it was like 10 feet long, it would take like hours to extend. But if the cylinder was tiny, so absolutely depending on the size. So, but what we take a look at here is, let me go back to this slide. I don't have to go back to the slide, just explain it to you. What we've got here is that if we select a larger cylinder, it's going to cost us more money than just going over and turning the pressure up just a little bit. No big deal. And this costs you anything. Okay. So it'll cost a little bit more to buy a larger cylinder, but it may be that we're maybe stressing it out, because cranking up the pressure to 110, 115 psi is right at the edge of the threshold of that system. And you might actually be stressing your compressor a little bit. Like, it's making everything work a little harder. So it may actually be better to go buy another cylinder that's a little larger. You may pay a little bit more money for it, but essentially in the end, it's stressing your system less. So that may be good, but you know what? If your system is set to 80 or 70 or whatever, and it's easy to turn it up, it's a nice, easy, simple solution. So there's no exact yes or exact no, but it's good to talk about all of the different variables and all of the different options. So depending on the exact application, there's no correct answer. The correct answer ultimately is to make your system that's going to function better and last longer. But function better is essentially the first thing. So last longer and price, those are kind of linked together. So if it's going to cost you a little bit more, but it's going to last longer, it's probably worth it. But if you're only going to run the thing a few times, you might as well just over pressurize it and just crank it up just so it kind of works and does what it needs to do. Functionality generally is the biggest deal, especially when you're dealing with some kind of situation where you're producing parts and your downtime for replacing something is going to take like it's going to cost you a lot of money, maybe $1,000 just for like a minute downtime, or maybe a few $1,000s. So you may want to say, you know what, I don't mind spending an extra $22 for a cylinder that's larger, especially if it's going to last me another year or whatever. So lots of different factors, absolutely. But I mean, you know what? It's also just good to say, well, I'm just going to crank up the pressure, make it work better, depending on the different situations. So can larger cylinder because we can withstand higher pressures. Therefore, what do we use a larger cylinder because? Okay. Do we use a larger cylinder because they can handle larger pressures? Sorry, Sonal, you're going to have to explain that. Who told you that? Therefore, more force without higher flow rate will make up for the larger volume. Do you know what? Yes or no? Essentially, it all depends. But you have made the assumption that a larger cylinder can handle higher pressures. And I would say, actually, a smaller cylinder can handle larger pressures because force and pressure are linked to surface area. Okay, so essentially what's going on is that if I were to take this and find the surface area of this whole thing, it's much larger than the surface area in that little tiny cylinder. So essentially, if I put 100 psi in here or 100 psi in the other one, this has got a lot more force trying to break it. Yeah, so the larger the cylinder, actually, the more fragile it is. Even if you make it out of a thicker steel, the dimensional size creates tremendous forces, much larger, because area is cubic, is a squared factor. There you go. So pressure therefore can move output, higher flow rate will make up for the lost volume. So the larger volume. So pressure lag. So essentially, if you have a higher volume, you will have a greater pressure lag, even if you crank the pressure up. It's a percentage of the pressure lag. So it's all a matter of kind of dynamics and figuring things out. Ultimately, however it works, again, you want to find a solution that gets the job done just faster, better, and just it finally gets your job done. So essentially, choosing a larger cylinder, it's going to extend more slowly, but if you do crank up the pressure, then it will extend more quickly. But if you cranked up the pressure, then you would actually have too much force. It's a whole balance, eh? Okay, guys, so let's go in. That was a really good discussion. I'm glad. Dude, I so wish that we were together in a classroom. Anyway, let's just move on. We're going to deal with it. We'll move on with life. Okay, so I got a question here. Let me go back to this question here. I have a doubt. Does the force of the cylinder action on the clamp if we change the bore diameter to a bigger one? Yeah, of course. So what's going to happen is if we change the bore diameter to a bigger one, but I mean, we're dealing with underforce. We've calculated that if we use 100 psi and we use a 2-inch cylinder, all we get is 314 pounds of force. It's not enough. So we're going to use a larger cylinder. And in the calculation of that larger cylinder, we may find that we are going to have 162 pounds of force. And then we're going to go, oh, that's too much. Okay, easy. I can just go over the pressure regulator, just turn it down, which is actually less stress on the system. I just turn the pressure down. So I'm going to adjust the pressure until it applies the correct amount of force. So yeah, it's important to take the size into note because it's going to make it. Okay, here we go. So I will share my screen and then I will buzz over to here and oh no, wait, wrong screen. Sorry guys. I'm still not used to these 3 screens. Okay, good. So we're almost there, dude. Like we're pretty much just. Let me just jump off of this. It was a good discussion. Actually, I may leave this in here because it really brought a really good discussion. I'm going to leave it in. Okay, let's move on. Now, get this. The distance that it travels, this is the rod travel, okay, is the rod travel distance. In this case, well, I can't talk. In this case, it's the clamping distance. It's not the stroke. Huh, maybe that's important for the quiz. Huh. Okay, let's continue on. So the distance is the distance that it moves. That's fine. We know the clamping distance. We wrote it down somewhere else. And now we can calculate the displacement here. So this is going on. So essentially it's 7.5 inches, and we can get that from here with the description of the operation. The clamping distance is 7.5 inches. Okay, good. So we're just putting that in there, and I'm calculating that. Okay, that's fine. Now, the retraction displacement is a little smaller because the rod's in the way. So the extension is 23, and the retraction is 17 because there's less air requiring to retract this. And of course, yes, there is less force, but we don't care about the force of retraction. We're clamping in extension. Okay, good. Now I'm going to do my time chart. The whole cycle takes 12 seconds because I know that there's this delay time in between, and then there's this whole thing. Oh, right. I had led you earlier to believe that the lag time was before this, but it's not. Sometimes we do. Sometimes we have a different time between cycles, but that has to do with kind of a variation in the loop, where essentially it goes and does a different cycle and it comes back. We won't even talk about that. What I'm saying here is this whole thing doesn't matter how long it takes the cylinder to extend. It doesn't matter how long it takes the cylinder to retract. The whole process takes 10 seconds. Okay, good. So it extends, holds for 10 seconds, and then retracts, and it goes back and forth, back and forth. The delay time is 2.5 seconds. It says so here, and this cycle repeats continuously. Okay, so one cycle, the full cycle time is 12.5 seconds. Oh, you know what? There's a whole formula for that, isn't there? Yeah, just plug it in. Okay, good. So that was my displacement for extension. This is my displacement for retraction, because we know it extends and retracts. The unit for that is in cubic inches. This is my conversion factor, 12.5 seconds. Oh, this is tiny, 0.115 cubic feet per minute. Dude, like if you go look up the specifications for a compressor, like even my lab compressor has probably got like 1 cubic feet per minute or half a cubic feet per minute. Like, you know what, dude, like my lab compressor could run this. The thing is, this is just one cylinder in an operation. This thing right here may be in a station with 10 or 15 of these. And there may be a whole bunch of other cylinders doing a bunch of things during this cycle time. So what's going on here is that even though this displacement is small, we may find that there are 10 or 15 cylinders with displacement like this, and we may end up with 2 or 3 cubic feet per minute. Some of the cylinders may be larger, some may be smaller, whatever it is. Often when we add them all up, we're going to get more than a cubic feet per minute. Okay, good. So now we're almost done, guys. I just need you to understand this. What's happening is that when we rate a compressor, the rating of the compressor is the air that comes out. And we're going to study that in week 9. See how that says week 9 there? Yeah, week 9. The compressors are going to be 2 weeks after the reading week. Pardon me. Anyway, whatever. I'll change that. So the flow rate coming out of here, the CFM, is the air we are really interested in. We're not interested in the air flow into here. We're interested in the air flow out of here, and that actually depends on what we set the pressure to, which is so cool. But I'm not going to talk about that until we get into the gas laws. We're just going to say whatever the air out of here is, that is the rating of the compressor. Okay, so what I want to do is I want to take this value here, and let's say I've got 20 of these cylinders in operation. So I'm going to multiply this by 20. Okay, so I'm going to have this number that's a large number, it's going to be 2 cubic feet per minute or whatever. I'm going to go over and I'm going to take a round, let's just say, pretend that this came out to however many of these cylinders I was using, it came out to exactly 2 feet per minute, right? So close enough to 2 feet per minute. Okay, good. So do I go get a compressor that can give me 2 feet per minute? No, it's going to stress the compressor because it's going to be on all the time. What I want to do is I want to go to at least minimum is 30%. I probably want to go to 50% over or possibly 100% over whatever I need. And then my compressor is a good compressor to use, at least 30%. Then I'm going to go buy a compressor that can give me 3 cubic feet per minute or 2.5 minimum. Then if I had a compressor that was 4 cubic feet per minute, I'd probably be best to go with that, but the least is 30, because anything lower than that, you're stressing your compressor. It's on all the time. Thank you for watching. You guys know what to do. There's going to be a worksheet that you guys should look at for all of this stuff so that you can write the quiz. You're welcome, sir. So remember that the actual rod travel is the distance we put into the formula. And that wasn't a lot of work. It's not a whole bunch of stuff to wrap your head around. All you need to do is just go and practice the worksheets and hit the quiz, and you're good. And also start the assignment. Is that really important? Yeah, like crazy important, guys. It's really a lot of work. Yeah, not actually just trying to scare you. It's actually a lot of work. That's it. Yeah. Okay, bye.